Hey everyone, my name is Jonathan Luton, and today I'm excited to present our paper, Track to Reconstruct and Reconstruct to Track, where we use 3D object reconstruction to improve multi-object tracking. This work was equally contributed to by myself and my colleague Tobias Fischer, and was done under the supervision of Professor Bastian Leiber. The core idea of this paper is that given an initial set of tracking results, we can improve upon this by using 3D reconstructions. For our initial tracks, we use a simple tracker that associates segmentation masks together over time based on the 2D motion consistency given by optical flow. These initial tracks are often much shorter than they should be, with objects being divided into multiple tracks, split whenever an object becomes occluded. We call these short initial tracks tracklets. We then perform 3D reconstruction on these tracklets and use this to extract the 3D motion of objects. We are then able to merge tracklets into longer tracks using the 3D motion extracted from these reconstructions and to fill in detections where they were possibly missed. The image in the bottom shows an example of our 3D tracking output and a 3D reconstruction of two different cars in the scene. Our algorithm takes a number of different inputs, which are all commonly available in robotic scenarios, such as depth estimates, ego motion estimates, optical flow estimates, and input object detections. In the first stage, we generate our initial tracking results by first calculating a segmentation mask for each detection using a bounding box to mask segmentation network. We then warp these masks forward in time using the transformation defined by optical flow. If these warp masks overlap with any mask in the next frame, we merge these masks together into the same tracklet. The simple procedure gives us our initial tracking results. In order to improve upon these results, we then perform 3D reconstruction-based tracking. We first estimate a global static 3D scene and project the pixels from every frame into 3D global coordinates. We then calculate a dynamic 3D reconstruction for each tracklet by fusing all of the 3D points from every time step into a single consistent 3D reconstruction. This also gives us the 3D motion of objects throughout the scene. We are then able to merge tracklets together into longer tracks if they have consistent 3D motion. We are also able to fill detections between merged tracklets if the detector missed objects in between. Finally, we can combine all of our results into a global dynamic scene reconstruction. Our 3D object reconstruction performs extremely well, as seen in the image here. For each object, on the right, every pixel for a whole tracklet is displayed, projected into global 3D space. As you can see, the objects are moving. On the left for each object is the result of our 3D reconstruction for these objects. All of the same pixels are displayed, except now they are in an object-centric 3D space. Our reconstruction is extremely accurate for cars. For pedestrians, the reconstructions are a little more blurry, as we don't specifically deal with the articulated motions of people. However, our algorithm still captures the overall 3D motion of people extremely well, which is enough to do accurate tracking in 3D. To calculate these reconstructions, we estimate a set of homogeneous transformations between objects in consecutive frames. We use optical flow to find pairs of corresponding pixels between the object masks in two time steps. These correspondences give us the 3D motion of different points on an object. Using a robust subset of these points, we then run a robust optimization algorithm to determine the best fit homogeneous transformation that defines the motion of the object between these two frames, in terms of both translation and rotation. Over the short tracklets, fitting these transformations frame by frame results in accurate reconstruction over whole tracklets without significant drift. The dynamic 3D reconstructions for objects gives us the 3D motion of those objects. The motion is defined by the transformation which fuses the objects into a single reconstruction. We then use this 3D motion to merge tracklets into longer tracks. We extrapolate the 3D motion for objects both forward and backward in time. If two tracklets have 3D motion which are consistent with one another, they are merged together into a longer track. We are also able to detect if the object is present between two merged tracklets and fill in potentially missing detections. To do this, we take the interpolated 3D bounding box, project it to a 2D bounding box, calculate a segmentation mask using our box-to-mask network, and then checking if the pixels in this mask are unprojected into our extrapolated 3D bounding box. This determines if an object was actually occluded or if it simply wasn't detected and should have been. The image in this slide shows this process. In the top row, the car in the background is split into two tracklets. In the middle row, we calculate the 3D location of the reconstructed object in each time step and estimate the interpolated 3D bounding box for the frames between. This shows that the two tracklets have consistent 3D motion and should be merged. The bottom row then shows the final merge tracking result with one of the missing detections filled in between. Our reconstruction-based tracker performs extremely well on tracking benchmarks. It sets a new state-of-the-art for both bounding box and segmentation mask tracking for cars and pedestrians on the KIDI tracking and KIDI MOTS benchmarks. We show huge improvement in the number of ID switches over the 2D baseline results over the initial tracks. The number of ID switches is reduced by approximately half compared to the results of the initial tracks. We perform a number of interesting ablations and extensions to our method. The graph shows the results when adjusting the maximum number of frames between tracklets that are allowed to be merged. When this is 0, no tracklet merging takes place, and the results are the same as for the initial tracks. As we allow tracklet merging and infilling for up to a 20-frame gap between tracklets, the results continue to improve, and as more and more objects that were incorrectly split into multiple tracks are merged. Going beyond 20 frames, up to 60 frames, tracklet merging still remains accurate, but the infilling starts to create more false positive detections. Beyond 60 frames, the algorithm starts to merge tracks incorrectly also. In our algorithm, we choose to use a 15 time step window. Thus, our tracker is able to track objects through complete occlusion of up to 15 frames. We also run experiments with different input modalities, e.g. using different depth estimates, e.g. LiDAR, stereo, and monocular single image depth prediction networks. Our 3D reconstruction method performs extremely well for all of these different inputs, even when depth estimates are extremely noisy, such as when using monocular depth. Finally, we also present an online version of our reconstruction-based tracking for use in online scenarios. Let's look at some visual results. I would like you to focus on the green car in the background. The results that we're seeing are the initial 2D tracking results. As you can see, the green car in the background changes its IDs multiple times over the video. In fact, this object is split up into 4 different tracklets in this short 10-second video. This is the result of our initial tracking of our initial tracks. Now we can see the results after applying our 3D reconstruction-based tracking. We can see for that same car in the background, it remains a constant ID as all of the 4 tracklets have been merged into one consistent track. Let's look at another example. Let's focus on the 2 cars on the left, a red and a green one. As we see, with the initial 2D tracking results, they change IDs 2 times, resulting in, for the 2 objects, 6 different tracklets. However, now, after applying our 3D reconstruction-based tracking method, the object IDs remain consistent, even through multiple occlusions. Let's look at one final example. Please focus on the small purple car in the far background, somewhere near the middle of the image. In the initial tracking results, this car changes IDs 7 times to be 8 different tracklets. Every time it is occluded, it changes IDs. As you can see now, it changes again and again and again and again until finally the end of the sequence. However, with our 3D reconstruction-based tracking, for this object, we are able to improve the results from being fragmented into 8 different tracklets to being fragmented into only 2. Our algorithm isn't perfect, but it works extremely well. Thank you for listening. Our paper and code are available.